If you haven't seen the last video, please go back and watch it quickly. In that video, I provided you an example for you to practice and asked you to observe if you noticed anything interesting, such as whether union or intersection is commutative. Is B intersection A also a subset of A and B? And B and A subset of B union A, along with so many other properties. All right, so it's time to answer these questions. A set A subset of B? How do we prove it? So we start by taking an element X in A, and then we prove that X belongs to B. If we are successfully able to prove this, then we say that A is a subset of B. So we take a random element in A and we prove that it is in B. Awesome. So let's start with the proof of the very first property, which is that if we have any two sets X and Y, then X is contained in the union of X and Y. Alternatively, it can also be said that X is a subset of X union Y. So how are we going to prove it? So we will start by taking a random element in X, and we will prove that X belongs to X union Y. Okay, the proof is very trivial. So we start by taking an element small x in the set X. And now, if X belongs to X, then small x will definitely belong to X union Y by the definition of union of two sets, because union of two set contain all the elements of both the set. So if small x is in the set X, then small x will be for sure in X union Y. And if since we have proved this, so we have that set X is a subset of X union Y. Isn't it simple? Okay, let's prove another property, that X intersection Y is a subset of X. So we take a random element small x in X intersection Y. Now, by the definition of intersection of two sets, we know that if X belong to X intersection Y, then X will definitely belong to X, set X and set Y, because X intersection Y contains all the elements that are in both the sets X and Y. So if small x belongs to the intersection, then X has to belong to X as well as X has to belong to Y. Now, it means that small x belongs to the set X, which means that X intersection Y is a subset of the set X. Perfect. Now, I want you all to try proving that Y is a subset of X union Y and X intersection Y is also a subset of Y. Just follow the steps for which I have proved that X is a subset of X union Y and X intersection Y is a subset of X. Follow these steps and you should be able to do it. Try it on your own. Well, let me prove another property for you all, which is union is commutative, which means that if we have two sets A and B, then A union B is equals to B union A. Okay, so what are we trying to basically do here? We are trying to prove that a set A union B is equals to the set B union A. Okay, so we'll use the fact over here. The fact which we're going to use here is that if we have two sets X and Y, they are equal if and only if X is a subset of Y and Y is a subset of X. This is the definition which we are going to do. So now the first thing is to prove that A union B is contained in B union A, and the second thing would be to prove that B union A is a subset of A union B. And this is why I started the proof by taking an element x in A union B, because now our goal is to prove that this small x belongs to B union A. Because if we prove that, then we would have that A union B is a subset of B union A. And then we're going to prove the other way around, that B union A is a subset of A union B, and we will have the property that, okay, both these sets are equal. Okay, so we started by taking an element x in A union B. Okay, so now if x belongs to A union B, then x will belong to either A, or x belongs to the set B, or x belongs to both the sets A and B. Because it's union, and union means all the possible elements of the set A and B. So if x belongs to A union B, it means that x either belongs to A or to B or to both the sets. So now we will do it in cases. So the case one is that if x belongs to A. Now if x belongs to the set A, then x will belong to B union A. Because what is B union A? B union A, again, contain all the elements that are both in B and A. So if x belongs to A, then x definitely will belong to B union A. Case 2. If x belongs to B, then x belongs to, again, B union A. Because union means that if x either has to belong to any of these sets or both the sets. So if x belongs to B, then also we will have that x belongs to B union A. And if x belongs to both A and B, then x again belongs to B union A, because now it is in both the sets. So it will definitely be in B union A. Perfect. So now what have we proved? We started with the element x in A union B. And we have proved that this x belongs to B union A. So what have we proved? We have proved that A union B is a subset of B union A. Perfect. And now we have to prove the other way around, which is that B union A is a subset of A union B. Okay, the proof is very much similar to what we have done here. So you will start by taking an element x in B union A. So we have to prove now that B union A is a subset of A union B. So we will prove this by taking an element x in B union A, similar to what we have done above. And if x belongs to B union A, we will have three cases, that either x belongs to just B, or x just belongs to A, or x belongs to both the sets A and B. In either of these three cases, we will have that if x just belongs to B, then also it should belong to A union B. If x just belongs to A, then also it will belong to A union B. And if x belongs to both these sets, A and B, then also it belongs to union of these two sets. Therefore, you all should be, now try this on your own. I have just given you all the hint. Actually, I've given you the proof. I've just not written in the slide. So now just follow the steps which we have done to prove that A union B is a subset of B union A. Follow these steps and you should be able to prove this. Perfect. And since A union B is a subset of B union A, B union A is a subset of A union B, you will use this definition that if x and y both are subsets of each other, we say that x and y are equal. Therefore, A union B would be equals to B union A. Isn't it simple? Okay. The next property which we're going to prove is that intersection is commutative, which means that A intersection B is equals to B intersection A. We'll use the similar thing which we have done in the last proof. That is, we will prove that A intersection B is a subset of B intersection A. We will prove that B intersection A is a subset of A intersection B, and we will have our proof. So now we'll start by proving, we'll first prove that A intersection B is a subset of B intersection A. So how do we do that? We take any random element into A intersection B. If X belongs to A intersection B, then X belongs to A and X belongs to B. Perfect. If X belongs to both the elements, then it is similar to like this statement is similar to X belongs to B and X belongs to A, which is that X belongs to B intersection A. So we started with X belongs to A intersection B, and we have proved that X belongs to B intersection A. Okay, so we have proved that A intersection B is a subset of B intersection A. Okay, so now if you look at this proof carefully, I have used if and only if arrow. So when you see the arrow on both the sides, it means that X union X belongs to A union A intersection B. This should be intersection. This statement implies X belongs to A and X belongs to B. And it also means that if we have X belongs to A and X belongs to B, it also means that X belongs to A intersection B. So whenever you see arrow on both the side, it means that the first statement implies the second statement and the second statement implies the first statement. So if you see in the entire proof, I have used the arrow, I have used if and only if arrow, which means that the first statement implies second, second implies third, third implies fourth. Now, in order to prove the other way around, we don't have to do it similarly. Since we have used the arrow on both the sides, it means that the other way around would follow the step similarly, but in the reversed manner. So now you will start with X belongs to B intersection A. This arrow means you go to third, this statement third. Now this arrow would take you the second, and this arrow would take you to the first statement. So now you don't have to do it separately. In this case of union, we just used arrow on the right-hand side, on the right side. Therefore, we did both the parts separately. So now here we have used if and only if condition, which is the arrow on the both sides, and we have proved that yes, if A intersection B is also a subset of B intersection A, B intersection A is also a subset of A intersection B, therefore A intersection B is equals to B intersection A. Okay, which is that intersection of two sets is equals to the set itself, which is the idempotent condition. So how do we do that? Whenever you see equality sign, remember that you have to use the definition of equal sets, that two sets are equal if one is the subset of the other and the second is also the subset of the first one. Well, here we have to prove that A intersection A is a subset of A and A is a subset of A intersection A. How do we prove it? So we start by taking an element in A intersection A, and we will have to prove that this X belongs to A. Now remember, again, I'm using here if and only if condition. So I don't have to do both the parts separately. If you use arrow on just one side, then you will have to do it separately. Now the arrows are on both the side, which means that if X belongs to A intersection A, then it implies that X belongs to A and X belongs to A. Now, the arrow on the left side means that if you have this statement that X belongs to A and X belongs to A, it will imply the first statement, which is X belongs to A intersection A. Okay, perfect. Now, it further implies that X belongs to A. Now, again, we have used if and only if condition. If you have second condition that X belongs to A and X belongs to A, it implies X belongs to A. Similarly, if you have third statement that X belongs to A, then the left arrow will make it that it also means x belongs to A and x belongs to A. Okay, so now what we have done, we have proved that A intersection A is a subset of A and A is a subset of A intersection A, both the thing at the same time. And therefore, now we have that A intersection A is equals to A. Perfect. Now, I would like you all to try the case of A union A is equals to A yourself. We will follow the same steps. We'll start by taking an element X in A union A, and we will have to prove that X belongs to A. Now remember, if X belongs to A union A, it means that X either belongs to A or X belongs to A or X belongs. If you think about it carefully, it just means that X belongs to A. So again, while proving this, you can just use if and only if sign, and you can prove both the sides at the same time, and you don't have to do it separately. Again, next property which we are going to prove is that A intersection A complement is equals to empty. Now, this is something which we observed from the example. How can we prove this statement? Well, the proof of this is it's proof by contradiction. So we start by saying that, let's say that it is not empty. Let's say that A intersection A complement is not empty. What does it mean? Something is not empty means that the intersection has some element. So we start the proof by saying that A intersection A complement is not empty. Again, so we are doing it because we are trying to prove this property by contradiction. So we start by claiming that let A intersection A complement is not empty. Let's say that it is not true. If A intersection A complement is not empty, it means that there is some element, there is at least one element in common. Okay, which means, let's say that X is an element which is in A intersection A complement. Again, A intersection A complement non-empty means there is at least one element in the intersection of A and A complement. So if we start by taking X in A intersection A complement, if X belongs to A and A intersection A complement, it implies that because it is in the intersection, it implies that X belongs to A as well as X belongs to A complement. Now, remember, we have AND over here. Whenever we have AND, it means intersection. It means elements are, this X is a common element in both the set. It means intersection. Whenever we have intersection, we have word AND. Whenever we have union, we have word OR. Here we have AND, which means X is the common element in both the sets, which means X belongs to A and X belongs to A complement. Now look at this statement. X belongs to A and X belongs to A complement. Let's try to understand what is the meaning of X belongs to A complement. So what is the definition of A complement? A complement contains all the elements from the universal set that are not in A, which means that basically X in A complement implies X does not belongs to A. Just this statement, X belongs to A complement. Now, what does it mean? It means that X belongs to A and X does not belongs to A, which is a contradiction because this thing cannot happen at the same time, that you have an element and you are getting that it belongs to the set and it does not belongs to the set, which is just absurd, which is a contradiction. And therefore, you would say that A intersection A complement is empty. There cannot be any element or in common in A and A complement set. Okay, so this is how we prove A intersection A complement is empty. Okay, let's move to the next proof, which says that complement of a set, if you take complement of that set again, so if you take complement of a set, you get the set itself. Again, as I said, whenever you have to prove equality, you use the definition that two sets are equal when X is a subset of Y and Y is a subset of X. So two sets are equal if both the sets are the subset of each other. So if we have to prove that, then we'll have to prove that A complement is a subset of A and A is a subset of A complement. How do we do that? We take an element X in A complement. If X belongs to A complement, that means X belongs to, that it contains, like X belongs to the universal set and X does not belong to A complement. That's the definition of complement of a set. That complement of a set contains all the elements from the universal set that are not in the set. Okay, now again, see, we have used if and only if condition, which means that X belongs to A complement implies this. And if you have this condition, it implies X belongs to A complement. Both these statements imply each other. Now, if you have X belongs to omega and X does not belong to A complement, it further implies that X belongs to universal set. And if X does not belong to A complement, it means that X belongs to A. Okay, again, we have if and only if sign over here. Remember, which means that third statement also implies the second statement. Now, what does this statement means? That X belongs to universal set and X belongs to A. It means that X belongs to the set A. Okay, because whenever we have and, it means that X belongs to A intersection omega, which is A. So now we have if and only if condition. So we don't have to prove both the like A complement is a subset of A and A is a subset of A complement separately. And we have the proof of the property that complement of a set is a set itself. Awesome. Next property, which is the difference between two sets A and B is a subset of A. Now, take an element X in A intersection B. If you have X in A intersection B, it would imply that X belongs to A and X does not belongs to B, because A difference between A and B means that you will get rid of all the elements from A that are in B. So you only write all elements of A that are not in B. Now, if you have that condition, it means X belongs to A and you have that A intersection A complement B is contained in A. Let's prove some interesting properties now. The properties which we are going to prove now are not difficult, but very interesting to follow. Okay, so now see, we have four sets. We have set X, we have set Y, A, and B. And it's given to us that X is a subset of Y and A is a subset of B. So these are the two conditions which are given to us, that X is a subset of Y and A is a subset of B. And we have to prove that X union A is a subset of Y union B. Okay, now whenever we have to prove that something is a subset of something, what do? We start by taking an element in the first set, and we will prove that if that random element belongs to the second set or not. If it belongs, we say that the first set is a subset of the second set. If it does not belong, then we cannot really say that. Okay, So let's start, since here we have to prove that X union A is a subset of Y union B, we will start by taking any random element small x in X union A. Now, if X, small x belongs to X union A, what does it mean? It means that X either belongs to capital X or it belongs to A, or it belongs to both the sets X and A. So there are three cases. X either just belongs to the set X, X either just belongs to the set Y, or it belongs to both the set X and A. So let's start with the first case, which is when X, small x belongs to the set X. If X belongs to the set X, what is the given condition? The given condition is that X is a subset of Y. So if small x belongs to the set X and X is a subset of Y, we have that this element X also belongs to the set Y. Okay, now if X belongs to Y, then X will belong to Y, or X belongs to B. Basically, it means that X belongs to Y union B. Okay, because Y union B is X either belongs to Y or B. So X belongs to Y implies that X belongs to Y union B. You can actually, it's okay if you don't write this line X belongs to Y or X belongs to B. You can just write the final line, which means that X belongs to Y implies that X belongs to Y union B. Now remember, this arrow is just on the right side, which means that the first statement implies the second. The second implies the third. This statement implies the fourth. It does not, you cannot say that the fourth implies the third statement, because this is not if and only if condition. It is just the arrow on the right side. Okay, so that was the first case, which is when the element X belongs to X. Let's quickly have a look what happens when this small x belongs to the set A. If X belongs to the set A, it is given to us that A is a subset of B. Okay, so this is A, this is not X, this is A is a subset of B. In that case, we will have that since X belongs to A is a subset of B, we will have that X belongs to the set B, which means that X belongs to union of B and Y. Okay, and the case third would be if X belongs to X and X belongs to A, like if X belongs to both the sets, then we have X is a subset of Y, we have A is a subset of B, therefore we have X belongs to the set Y, X belongs to the subset B, X belongs to the set B. Since we have an AND condition over here, it means that it will definitely belong to the union of Y and B, and therefore we have proved that. We started with the assumption that let X belongs to X union B, and we have, in all the three cases, we have successfully proved that X belongs to Y union B. B union Y is because union is commutative. This B union Y also means Y union B. And also third case, we have Y union B. So from all three cases, we can conclude that X union A is contained in Y union B. That is, if now try proving all these properties. Do not get scared looking at all these properties. Trust me, these are not very difficult. These are very easy to prove. If you look at the first property, so there are different ways to prove this property. I will give you the hint for the first one. So if we have A, B, and S B sets, and A is a subset of B, then we have to prove that A union S is a subset of B union S. So what are you going to do? You're going to start with an element X in A union S. And you will have to prove that that element X belongs to B union S. Now, if X belongs to A union S, you will have three cases. Either X belongs to A, or X belongs to S, or X belongs to both the sets A and S. Now, if X just belongs to A is a subset of B, then X will belong to B. And X will therefore belong to B union S. If X just belongs to S, then clearly X will belong to B union S. And if X belongs to both the sets, then since A is a subset of B, X will belong to B and X belongs to S. Therefore, X belongs to B union S. Again, we have to use the same thing which we have been using so far, that to prove that one is a subset of other, you take a random element X in one set and you prove that it belongs to the second set. Now, for the second property, if you see, it is very interesting. You have to prove that that A is a subset of B if and only if A union B is contained in B. This property, I have proved it over here. But I will quickly give you a hint. How can you prove one side? Now, if you look at the property above this, which is if A is a subset of B, which is if A is a subset of B, then A union S is contained in B union S. So take S is equals to B. If you take S is equals to B, you will have A union B, which is this, and B union B is B, which we have already proved. So one side can be proved using the property we have listed over here. Okay, the rest of the properties also follows the proof which I have mentioned before. So just let's prove the first one, the second property, which is that A and B are two sets, and we have to prove that A is a subset of B if and only if A union B is equals to B. Now, if you look here carefully, we have if and only if sign, which means that we have to first assume that A is a subset of B, and we have to prove this property. And then conversely, we will assume that this hold, and we will have to prove that A is a subset of B. Okay, so let's start the proof. So let's assume first that A is a subset of B. We will prove that A union B is equals to B. That is our claim, that A union B is equals to B. Now, what are we trying to do? We are trying to prove that A union B is equals to B. Again, how do we prove this? We always we can prove this statement using the property I have stated before. Okay, so what we have? We have that A is a subset of B. A is a subset of B. So if you take if you take A union B, B union B, again, what I have done over here, if you quickly go back to this property, the first property, it says that if A is a subset of B, then A intersection S is a subset of B intersection S. Here we are taking S is equals to B. This is what we are doing. This is the first task, right? So here we have assumed that A is a subset of B. We are using that property. We have taken S is equals to B. So A is a subset of B implies A union B is a subset of B union B. Okay. Now, using the idempotency, we have that B union B is equals to B, and we have that A union B is contained in B. Okay, so now, but what do we have to prove? We have to prove that A union B is equals to B. How do we prove that two sets are equal? We can prove that two sets are equal by showing that both the sets are subset of each other. So one side we have proved. We have proved that A union B is a subset of B. It remains to prove that B is also a subset of A union B. Now, how do we prove that B is a subset of A union B? Okay, it is very easy. So we use the fact over here that if we have two sets A and B, then both the sets are subset of union of those two sets. The very first property we proved, that if we have A and B as two sets, then A is a subset of A union B and B is a subset of A union B. It is by the definition of union of two sets, right? Okay, so now we have that A union B is a subset of B, B is a subset of A union B, and thus we have the result that A union B is equals to B. Now, okay, so we started with the assumption that A is a subset of B, and we have proved this part that A union B is equals to B. Now remember, we have if and only if condition. Wherever you see IFF, it means if and only if condition. It means that the reverse, that you will have to prove the result both sides. We have already proved A is a subset of B implies A union B is equals to B, and now we will start by assuming that A union B is equals to B. We will prove the other way around. We'll prove that if A union B is equals to B, and now we're going to prove that A is a subset of B. Okay, now how can we clearly say from here that if A union B is equals to B, then A is contained in B? Okay, now remember, A is a subset of A union B. So we have this from the definition of union of two sets, that if we have two sets A and B, then A is a subset of A union B. So we will have this A is a subset of A union B, and A union B is equals to B, which means that A is a subset of B as well. Okay, so what did we really do here? So we started with the assumption that now A union B is equals to B, and we have to prove that A is a subset of B. So we use the definition of union of two sets, and we say that A is always a subset of A union B. Now, since A union B is equals to B, therefore A is also a subset of B. We have proved both the parts, and we have our proof. Okay, now try proving that A union A complement is omega, A union empty set is A union universal set is universal set. I will give you a hint. How would you prove that? You will just prove that I will just give you the hint for the last part, and I will leave for you guys to prove the first two part. Okay, so we have A union omega is omega. So what do we have? If A is a subset of B, we always know that every set is a subset of universal set. So A is a subset of universal set. Since this part is true, we have that A union B is B, which means that A union omega will be equals to omega. And this proves this part. We will use the same fact in the first two part as well. So I leave it to you guys as I leave the first two for you guys to practice, try it, and let me know on the comment box if you all were able to do it or not. Okay, let's move forward. Okay, let's prove that intersection with subset is subset. So if you look in the last property, we proved that union with superset is superset, which means that if A is a subset of B, then A union B is equals to B. Whereas here we are saying that intersection with subset is subset. Here, if A is a subset of B, then intersection of A with B will give you the subset A. Okay, again, we have an if and only if condition over here. So what do we have to do? We will have to start by proving A is a subset, by assuming this A is a subset of B true, and we will prove that A intersection B is equals to A. Conversely, we will say that A intersection B is equals to A is true, and we will prove the first part, which is A is a subset of B. Okay, let's start with the assumption that A is a subset of B. So what do we have to prove? We have to prove that A intersection B is equals to A. Okay, now what do we have to prove? We have to prove that A intersection B is equals to A. How do we prove two sets are equal? We prove two sets are equal by proving that both these sets are subset of each other. So what do we have to do here? We have to prove that A intersection B is a subset of A, and we have to prove that A is a subset of A intersection B. So we start by, again, the assumption is that A is a subset of B. If A is a subset of B, so now take intersection both sides. Now you all must be wondering that which property did we really apply over here? Okay, so if you quickly go back to this slide where I asked you to prove these results. Okay, so the first two results are for union. The third result is a result which I have written and asked you all to try for the intersection. Now remember, the result, the proof follows the proof. You would prove it similarly to how you proved this. So this is that if X is contained in Y, A is a subset of B, then X union A is a subset of Y union B. Here in the third, we have that X is a subset of Y, A is a subset of B. We just have to prove that intersection of X and A is a subset of Y intersection B. Now remember, you would prove it by, you would follow the steps which I have done over here to prove this third property. And trust me, the proof is really simple. You would start by taking an element X in X intersection A, and you will have to prove that it belongs to Y intersection B. And how do you do that? If X belongs to X intersection A, because we have intersection sign, we will definitely have that small x, that element belongs to both the sets X as well as A. Now X is a subset of Y, therefore X will belongs to Y. A is a subset of B, therefore X will belongs to B, which will imply that X belongs to Y intersection B. Again, pretty easy. The proof is pretty easy. You just need to take an element in the first set, and you have to prove that it belongs to the second set. Similarly, you will prove the second property, and the third one is something which I am proving over there. Okay, so now what are we doing over there? So we have A, B, S to be three sets, and we have that A is subset of B, and then it holds that A intersection S is also a subset of B intersection X. Again, we use the same things. We take a set to prove this property. We take an element X in the first set, A intersection S. If we have this, we will have that X belongs to A and X belongs to S. A is contained in B, therefore X will belong to B. And since we have X belongs to B and X belongs to S, we will have that X belongs to B intersection S. Now remember, we are using this property. We are using the property that if A, B, S are three sets, and if A is a subset of B, then A intersection, if A is a subset of B, then A intersection S is a subset of B intersection S. Now, to prove the property for intersection, to prove that intersection with subset is subset, here we have the same assumption that A is contained in B. So we have A intersection S is contained in B intersection S. So we take S is equals to A over here. We take S is equals to A, and therefore we will have that A intersection A is contained in B intersection A. That is, A intersection A is a subset of B intersection A. Now we have seen the idempotency condition, and we will have that A intersection A is A. We have already seen the proof, and thus we have that A is a subset of A intersection B. Perfect, one part done. And now we have to prove that A intersection B is also a subset of A. How do we prove it? We use the fact that A intersection B, the intersection of two set, is always a subset of the individual sets of the original set. That if we have two sets A and B, then intersection of A and B is a subset of A, and A intersection B is a subset of B. We have already proved it. So now we have both the condition that A is a subset of A intersection B, A intersection B is a subset of A, and thus we have that A intersection B is equals to A. Awesome. Now for the other way around, what do? We assume the condition that A intersection B is equals to A, and we have to prove that A is a subset of B. So you start, whenever you have to prove this, what do? You take an element in X and you prove that that element belongs to B. So you take an element X in A. If X belongs to A, we have already assumed here that A is equals to A intersection B. So if you take X belongs to A, then X belongs to A intersection B. Now, using the definition of intersection of two sets, that if we have two sets A and B, then A intersection B is a subset of A as well as B. So if X belongs to A intersection B and A intersection B is a subset of B, therefore X belongs to B. And from there, we will have that A is a subset of B. So what did? We started by taking an element in X. Since A intersection B is equals to A, we will have that X belongs to A intersection B. Now we use the fact that intersection of two sets is contained in the set individual, in the original set. Therefore, X will belong to B because A intersection B is a subset of B and X belongs to B, and we have this condition. So we have proved both the sides. But for the first one, we have A intersection empty set. A intersection empty set, we know that empty set is a subset of every other set. Therefore, empty set is a subset, and we will have A intersection empty set to be empty set. Second statement, which is A intersection omega, it is equals to A. Why? Because A is a subset of omega, and using this property, we will have that A intersection omega is equals to the smaller set A. But for the first one, when we have three sets A, B, and C, then we have that union and intersection follows associative property as well. That means that if you take A intersection and then intersection of B and C, it is same as taking the intersection of A and B first and then finding the intersection of that with C. How do you prove that? We start by taking an element in A intersection B intersection C. Now, again, if you look here carefully, we have if and only if sign. So we have this arrow where we have arrows on both the sides, left side and right side. So X belongs to A intersection B intersection C implies X belongs to A and X belongs to B intersection C. Further, we have that X belongs to A. Now, what does this X belongs to B intersection C means? It means that X belongs to B and X belongs to C, right? We have intersection sign. Whenever we have intersection, it means that X belongs to both the sets. X is a common element. So what do we have basically? We have that X belongs to all the three sets. So it doesn't matter even if you flip the bracket because you have X as a common element in all the three sets. So instead of finding the intersection of the last two sets first, we can just flip the brackets and we can find the intersection of the first two sets. Again, we can only do this because X is a common element in all the three sets. So what do we have now? X belongs to A intersection B and X belongs to C. Now, if you look at this statement, it is similar to saying that X belongs to A intersection B intersection C. Okay, now again, this is an if and only if condition. Therefore, we have that A intersection B intersection C is a subset of A intersection B and then its intersection with C. And vice versa, it's true because we have an if and only if statement over here. And thus we have that intersection is associative. Now, I have left it for you all to prove that union is associative. Okay, so now distributive property. what is the distributive property? Distributive property is that A intersection B union C is equals to A intersection B union A intersection C. What does it mean? That if you take the union of B and C and then its intersection with A, it is similar to, the result would be same as taking the intersection of A and B first, and then its union with A and C, intersection of A and C. Again, whenever we have equal, we use the same logic that both the sets should be the subset of each other. To prove the subset thing, we start by taking an element in the first set, and we will have to prove that X belongs to the second set. Again, we are using if and only if condition, which means that first implies the second statement, second implies the fourth statement, which means that we don't have to prove that A intersection B union C is a subset of the second one, and the second one subset of A intersection B union C separately. We can just do it together because of if and only if condition over here. Okay. So now if X belongs to A intersection B union C, it implies that if and only if X belongs to A and X belongs to B union C. Okay. Now, just be attentive. What do we have next? We have that X belongs to B union C means X either belongs to B or X belongs to C. Now remember here, I have not written the condition when X belongs to both the set because it will be trivial. Usually, if you follow any books and other stuff, you will see that they would usually not include the condition when X belongs to both B and C, because if you include that condition, it becomes trivial that X belongs to all the subsets. So here, if that happens, that would be a trivial condition. Therefore, I have just not written it over here, and I have just written two cases that X belongs to B union C means either X belongs to B or X belongs to C. Okay. So now, what does it mean? It is similar to say that X belongs to A and X belongs to B, or X belongs to A and X belongs to C. Now see what I have done over here. So we have X belongs to A. In the third line, we have X belongs to A and X belongs to B or X belongs to C. This and means X belongs to A and X definitely has to belong here because we have an and. But out of these two, if X belongs to either of these set, then it would work. So what do we have? X definitely belongs to A and X belongs to B, or X definitely will have to belongs to A and X belongs to C. So the or condition becomes that like X belongs to B will definitely has to be true with X belongs to A, or X belongs to C and X belongs to A has to be true. So now this can further be written as X belongs to A intersection B or X belongs to A intersection C. What is or? Or is basically union. So we have X belongs to A intersection B union A intersection C. Do not get confused and do not overthink that why didn't we write X belongs to B and C both, because if we write X belongs to both B and C, then it would be a bit trivial because X belongs to A and then we will have X belongs to B and C. It means that X belongs to all the three sets. So anyway, that would be true. So that is a trivial condition. So we just stick to X either to B or X either to C. Perfect. Now, which gives us the proof. Now, again, see, we have if and only if condition. Therefore, we don't have to do it separately and we have the proof all together. Now, try proving this property. This is also a distributive property, but the only change is that here we have union. Here we have intersection. Now we have union over here. Here we had union, and now here we have intersection. All the other things are same. The proof will follow steps and you will get the proof. Okay, De Morgan's laws. De Morgan law is that if you take union of two sets A and B and take its complement, it is same as saying it is equals to A complement intersection B complement. Now, to follow the proof, what do? We do the same trick. If we have to prove equality, it means we have to prove that one set is a subset of other and the other one is a subset of the first one. And how do we prove subset? We take the element in the first set and we prove that it is the element of the second set as well. So we start by taking X belongs to A union B whole complement, which means that by the definition of complement of a set, which means that X belongs to universal set. It means all those elements from universal set that do not belong to A union B. Now, X do not belong to A union B means X does not belong to A and X does not belong to B. Remember, we have that X does not belongs to A union B. The negation would be that X does not belongs to A and X does not belongs to B. Why? Because if you have X belongs to A union B, it means that X either belongs to A or X belongs to B. But now if I'm saying that X does not belongs to A union B, it means that X neither belongs to A nor belongs to B. Because if X belongs to either of these two sets, then it has to be in the union, which means that now X is not in A and X is not in B. Now, what does X not in A means? That X belongs to A complement. And what does X not in B means? That X belongs to B complement. So what do we have? We have that X belongs to A complement and X belongs to B complement. And therefore, we have our proof that X belongs to A complement intersection B complement. Since we have used if and only if condition, we do not have to prove that A complement intersection B complement is a subset of A union B whole complement separately, and we have our proof. So this is the end of video 3. Goodbye.